After studying this module, you shall be able to know the different versatile applications of derivatives. You will learn the individual functions, understand their mathematical applications, and identify limitations of the important derivative applications.
In economics, derivatives play a vital role. In this module, we will talk about various important applications of derivatives such as 1. The extreme value theorem, which is used to determine whether a function has a maximum value and a minimum value in any given interval. Number 2. The mean value theorem, which is an extension of the intermediate value theorem and is used to find a point C belonging to the continuous interval AB, where the slope of the tangent at FC is equal to the slope of the line joining the endpoints of the interval. Number 3. Taylor's formula, which is often used in economics and is considered as one of the main results in mathematical analysis. Number 4. Newton's formula, which is used to compute the nth root of different numbers. Number 5. Second order and higher order derivatives, which are used to determine whether a function is concave or convex. Number 6. Cost functions, which are widely studied in economics and used to derive the marginal costs and average costs. Number 7. L'Hopital's rule, which is a standard method for systematic treatment of indeterminate forms, that is, the forms for which the limit cannot be found without further examination.
The important applications of derivatives constitute functions that involve the best way to accomplish some tasks. The extreme value theorem determines the maximum and the minimum value of a continuous function in a given interval. The mean value theorem is used to find a point C belonging to the continuous interval AB, where the tangent at FC is equal to the slope of the interval. Taylor's formula is considered as one of the main results in the mathematical analysis. Newton's law is used to compute the nth root of different numbers. Second order and higher order derivatives are used to determine whether a function is concave or convex. Cost functions are used to derive the average and the marginal cost. L'Hopital's rule is a standard method for the systematic treatment of indeterminate forms. Let us first start with extreme value theorem. In the application of critical points in a continuous function f, extreme value theorem determines both the maximum and minimum value in a closed interval ab. If f is continuous on a closed interval ab, then it has both a minimum and a maximum point. That is, there are real numbers c and d in ab, so that for every x in ab, fx is less than or equal to fc and fx is greater than and equal to fd. To understand mean value theorem, consider a function f defined on an interval ab and suppose that the graph of f is connected and without corners as shown. Because the graph of f joins a to b by a connected curve having a tangent at each point, it is geometrically plausible that for at least one value of x between a and b, the tangent to the graph at x should be parallel to the line AB. In the figure, epsilon appears to be such a value of x. Line AB has slope, so the condition for the tangent line at epsilon f epsilon to be parallel to line AB is that, in fact, epsilon can be chosen so that the vertical distance between epsilon f epsilon and AB is as large as possible. Thus, the mean value theorem states that if f is continuous in the closed bounded interval AB and differentiable in the open interval AB, then there exists at least one interior point epsilon in AB such that. Let us now understand Taylor's formula. It represents the mathematical approximation to fx about x equals a by an nth degree polynomial is given by. The polynomial on the right hand side of the equation is called the nth order Taylor polynomial. For x equals 0, the polynomial equation will be. The polynomial approximation is useful in relation to the known errors in results. Taylor's formula remedies this deficiency. Consider the approximation given for x equals 0, except at x equals 0, Function fx and the Taylor polynomial on the RHS are usually different. The difference between the two will depend on x as well as on n and is called the remainder. We denote it by Rn plus 1x. Hence, the Lagrange remainder theorem gives an important explicit formula for the remainder. Suppose f is n plus 1 times differentiable in an interval including 0 and x, then the remainder Rn plus 1x can be given by. Using this formula for Rn plus 1x in equation 1, we obtain Taylor's formula. Newton's binomial formula can be obtained using Taylor's formula. Applying Taylor's formula to fx equals 1 plus x raised to the power m. M is an arbitrary real number. We get for x greater than minus 1. Substituting into Taylor's formula gives us. To simplify the notation, we introduce the definition. Using this notation, we obtain Newton's binomial formula. M is an arbitrary real number and n is a positive integer. In a given function y equals fx, dy by dx is called the first derivative. The derivative of dy by dx is termed as the second derivative. The second order derivative is represented by. Similarly, the third derivative is d cube y by dx cube, and similarly it can go up to the nth derivative dny by dxn. The first, second, third, nth derivatives are also denoted by f dash x, f double dash x, f triple dash x, and so on up to fn x. The cost of production expressed as a function of the level of output x is termed as cost function written as Tc equals fx. The short run cost function can be derived from the short run production function. In short run, the quantities of certain inputs remain fixed while the quantities of others are variable. The cost of using fixed input factors is known as fixed cost, and the cost of using variable input factors is known as variable cost. Fixed cost does not vary with the level of output, that is, it remains constant whether a firm produces 0 or x greater than 0 units of output. On the other hand, variable cost increases as more and more units of output are produced. However, the variable cost is 0 when x equals 0, when the firm is not producing anything. The first derivative function measures the instantaneous rate of change in the function. The second derivative gives the rate of change in the first order derivative. Thus, if the second order derivative is greater than 0, the slope of the curve is increasing, and if it is less than 0, the slope of the curve is decreasing as we pass through the concerned point. The sign of the second derivative is related to the curvature of the function. When the second derivative is greater than 0 over a domain or its subset, the curve is strictly convex from below, and when it is less than 0, the curve is strictly concave from below. If it is greater than equal to or less than equal to 0, then the function is said to be weakly convex concave. Total cost is a sum of total fixed cost and total variable cost. The elasticity of the total cost, represented by mu, is given by the ratio of the proportionate change in the total cost C to proportionate change in output X. The elasticity of total cost equals d log C by d log X equals dC by dx multiplied by X by C equals dC by dx by C by X equals marginal cost by average cost. Further, we can show that elasticity of AC equals mu minus 1, which can also be written as MC minus AC by AC.
Let us now summarize the various concepts that we have learnt in this module. The extreme value theorem, which asserts that if a function f is continuous in a closed bounded interval AB, then it attains both a maximum value and a minimum value in the closed interval AB. 2. The mean value theorem states that if f is a continuous function in the closed bounded interval AB and differentiable in the open interval AB, then there exists at least one interior point xi in the open interval AB such that f dash xi is equal to fb minus fa upon b minus a. Number 3. The Taylor's formula. Fx is approximately equal to f of 0 plus x upon 1 factorial f dash 0 plus x square upon 2 factorial f double dash 0 plus x cube upon 3 factorial f triple dash 0 and so on up to x to the power n f n 0 upon n factorial plus x to the power n plus 1 upon n plus 1 factorial f n plus 1 c for some number c between 0 and x. Number 4, Newton's binomial formula. M is an arbitrary real number and n is a positive integer. This formula says 1 plus x to the power m is equal to 1 plus mc1 x plus mc2 x square plus so on mcn x to the power n plus mcn plus 1 x to the power n plus 1 into 1 plus xi to the power m minus n minus 1 for some xi between 0 and x with x greater than minus 1. 5. Cost functions where total cost Tc is equal to total fixed cost Tfc plus total variable cost Tvc and the marginal cost Mc is equal to dTx upon dx, which is further equal to d of Tvc upon dx. Number 6. The L'Hopital's rule, simple version. If f and g are differentiable at a, with fa is equal to ga is equal to 0 and g dash a is not equal to 0, then limit of fx upon gx as x tends to a is equal to f dash a upon g dash a.